Okay, good day, everyone. I'm so happy to be here as today we're talking all about the confidential computing with quite a nice and good topic. My name is Roman. I'm principal architect and I'm leading security community engagement at Red Hat. I also maintainer and contributor to open source and just try to make sure the security is reasonable and engineering centric in software development in general and in open source specifically. Today I have extremely small amount of time, 15 minutes, to talk about how to build confidential computing on an open source stack. All right, let's keep it going. First of all, as we enter in 2026, I think it's very, very important to mention that the world is changing and priorities are changing. If you would please have a look at the recent cloud security report by Red Hat, where 96% respondents said they have worries about the use of Gen AI in their cloud environments. On the other hand, 60% of companies surveyed have no AI governance at all. Quite scary, isn't it? Also, things like DORA, the EU regulation for financial entities and digital sovereignty, which actually goes beyond Europe in other regions as well. And also, we see the increasing amount of distributed AI training and remote AI inference, and etc. So that all makes us pretty confident to say confidential computing is at rescue, right? This is the recent IDC's confidential computing study in, I think it conducted last year, yes. And if you can see 75 overall, 75% of the respondents said that they either deployed it in production or piloting or testing use, which is quite a significant number, which brings us to understanding that we are switching over from the from the education and from the niche application of confidential computing to a real production deployment as we get in value of it. I don't have that much time to explain how it all works, but in general, keys for rescue confidential computing based on trusted execution environments that protects in-memory data from unauthorized entities. Basically, the four pillars or the four defining characteristics of TEs are memory encryption, isolation, remote attestation, and data integrity. But if you have a look on this picture, which is on the right-hand side, you can see that something is missing here. And of course, the TE are based on the hardware, right? On the hardware that should support execution of the workloads inside the secure enclave. But for today, with this presentation, I will try to show you how open source can actually help navigate this. And also I have a bonus slide about the open source hardware as well. I think that what you do should not dictate where or how you do it. This is our paradigm here at Red Hat, but I think it reflects across the industry. We want to have flexibility, but we want to have control on the other hand. So open source can help with all of this. And even with such relatively complicated technology as a confidential computing, open source enables the wide adoption of it. What are those key confidential computing communities? I would point out to three of them and others. Confidential computing consortium is a great avenue where we discuss all things confidential computing, define the standards, at least try to, and most importantly, encourage all of the vendors, both hardware and software vendors, to collaborate together to make sure confidential computing is standardized, accessible, and seamless for everybody. CNCF also have a good handle on the confidential computing, mostly with the confidential container project, which I will explain in details later on. And also there is a trusted computing group, which defines specifications mainly related to TPMs, trusted platform models, and measured boot processes. Of course, we have other communities that are somehow connected to confidential computing as well, like QEMU, libvirt, Lux, Linux kernel itself, and etc., etc. So those projects are instrumental in enabling confidential computing at scale. There are three main models of confidential computing based on who you trust, or kind of trust boundaries: confidential VM, confidential containers, and even more confidential clusters. For the purpose of this presentation, I will focus on confidential containers as one of the easiest way to build confidential computing capabilities for hybrid cloud environments. And of course, we're more than happy to have you on board. Please join us in all of these communities, as we really true value your feedback and contribution, and we couldn't have achieved the current level of maturity of confidential computing open source stack if there were no contributions. Please join us. We're really friendly and we don't bite. Now, I promised you to focus on confidential containers. Today, first, I want to start with how do I create a TEE, Trusted Execution Environment, using open source. And those three projects, KEMU, Kata containers, and confidential containers, can help on this. Kata containers is an open source community working to build a secure container runtime with the very light virtual machines. Don't be confused and don't be scared that we kind of spin off the virtual machine instead of containers. It really sounds like an actual container, but on the other hand, it provides stronger workload isolation by utilizing hardware virtualization as a second layer. Kata containers supports multiple hypervisors, including we call them type 2 hypervisors like KEMU, for example, and also type 1 hypervisors like KVM, and integrates with Containerd project among multiple others. Now, how do I actually utilize these projects to build the confidential VMs and confidential containers? This is the simplified picture that represents how it could be done by using confidential containers or COCO project. Kata containers actually can use a single configuration file, which contains everything, including the runtime, agent, and hypervisor configurations, and it acts as a runtime to manage container lifecycle within a specialized virtual machine, while KEMU acts as a local hypervisor. The COCO project, in general, aims to enable users to run containers inside trusted execution environments that are, powered in this particular example by containers on any Kubernetes cluster. And this is where I was referring to the flexibility, because when it comes to hybrid cloud environments, we don't want to have the limitations. We want to work it all across the hybrid fleet and independent of the vendor, independent of the installation. And COCO provides a common foundation for deploying containers inside VM or process-based TEEs. So now, once we build the confidential containers, right, using the confidential VMs, then the other part of the confidential computing is remote attestation. How can I trust a TE using also open source projects? And I want to bring two great open source projects here on the page. The Keylime, which supports runtime attestation, and it has integrations with the kernel's integrity management architecture. Basically, that is typically Keylime is used for remote boot attestations for TPM-based systems, or for like more flexible cases when you wanted to do something on your own and get more control over the operation system and the whole environment. Confidential containers, trusty projects, on contrary, optimized to act as an admission gate, and it seamlessly integrates into the containers and Kubernetes ecosystem. So all the links are here. I will not repeat the links on the following slides, but of course you can then access the slides and learn more about this. Now, how confidential computing attestation works with Trusty. The left side of this diagram includes the guest components running inside the TEE, including the attestation agent and confidential data hub. The right side includes the external components which the guests such as, for example, key broker service, attestation service, and the reference value provider service. We only have actually so low amount of time, but all of these acronyms actually maps to ETF RATS, Remote Attestation Procedures Architecture, and this is very important that trusty open source remote attestation tool maps to these standards to make it true confidential computing compatible. If we look at the full picture and how we can scale the deployment, on the left-hand side, you can see the hub cluster managing security, and it can contain the trusty, right, attestation service and key brokers service all in one, or actually they could be split based on the type how you deployed trusty, but for the simplification, they could be there. It can provide the reference values between the trusted infrastructure, and then when you run clusters that carry workloads, the confidential containers, even on untrusted infrastructure, it can ask attestation service and KBS for the evidence and for the attestation. It's very important to mention that for container VMs, there are a lot of restrictions still, and a lot of the security considerations that should be taken in account. For example, when it comes to how operating system image is handled, we must make sure that the CVM host, storage provider, or anyone else basically outside the TEE environment from compromising the image, because otherwise, imagine it could be easily compromised and tampered. There are a lot of other security considerations related to CVMs specifically. Don't want to dive into the details that much, but I want to leave you with the understanding that confidential containers consistency can make actually measurements achievable as the part of the resolving some of the security consideration that I mentioned before, like preventing tampering of confidential VM OS image, right? You can learn more about Coco use cases on the official website. Again, this is all free, open source, contributions are welcome. You can ask me a question, wait, is it really so hard to deploy? I would offer you the answer, no, it's not really hard to deploy, because when we talk within the community and also within the industry, typically it's relatively hard to explain what confidential computing means to the average person, but it is significantly simpler actually to deploy confidential computing, confidential containers specifically. There are so-called confidential containers or COCO validated patterns also available at GitHub. And these validated patterns can use Kubernetes cluster, for example, open source OKD, and well integrates with the CI/CD tools like Argo CD that can help you to spin up applications so that you can then utilize Open Cluster Manager, for example, for Kubernetes environment. And as I mentioned previously, Trusty and KMS, I mentioned that briefly, but key management storage is of course required as you kind of manage the keys or store the keys for Trusty. And then on the right-hand side, remember the previous picture, right? The left-hand side, data center hub. The right-hand side, a spoke or edge, the actual workloads. We can also utilize open source OCM agent and use Argo CD and Kata containers to run confidential applications on it. The icing on the cake that you can use these validated patterns as almost the one click. And this is all the instructions over there, so it's relatively easily deployable, which is good and justifies to the easier adoption of the technology. Finally, to wrap it up, I mentioned these hardware vendors, CPU vendors that we still rely on to actually execute, to support TE and to execute confidential workloads in the enclaves. But there are a number of the paper and research and researchers that are happening in the RISC-V community and also in the ARM related community. I just returned from FOSDEM, which is annual open source gathering in Brussels, Belgium, and there was the full dev room, like mini conference about the confidential computing, and there are a lot of interesting researchers were presented about how open source can be leveraged to enable or to unblock confidential computing implementations, both from low level to the confidential containers, like more cloud level. So that's been said. Hopefully, we will see one day when we can say truly that confidential computing stack could be built fully 100% on open source, which would be the dream, I think. But now, join us in building secure future for all open source way. Join the communities that I just mentioned, and don't hesitate to try it out following the links that I shared. I'm going to stop here. Thanks very much for your attention.
Thank you, Roman. Sorry for that rough start. I had like catastrophic failure across many different things. So I really appreciate your taking the baton forward. That was a really good overview. And of course, I am a super fan of open source. So I really appreciate you coming in and kicking us off.
Thank you. It was my pleasure.
All right. Thank you. See you soon. Okay, next I am going to bring on here Jerry Yu and my partner in crime here, Malini. Hold on, let me get her. Okay. Hello.
Hello,
No.
Risha.
Hey. Oh, good. Okay. So let me introduce you a little bit here. They are going to talk about getting started with Google Confidential VMs, which is also really great. So Malini, I crossed paths with when I was at Intel, actually both of these people. But at Intel, she was a cloud native architect. Previous to that, she was at VMware. Now she's here talking to us about confidential VMs. Jerry is at Intel. He's been there for 23 years. Confidential computing security architect. These two really know what they're talking about. So this will be another great sort of getting to understand sort of the parameters of confidential computing and really how to get started if that isn't something that you have done. So I am going to remove myself and then make sure that you can share your screen. So I'll remove myself.
Okay. And I'll try sharing our screen. Okay, hang on. To share. I don't know what's happening here. It's not what I wanted. Okay, I'm having few difficulties.
I think if you hit, Malini, if you hit screen.
I did?
Bottom, it should work.
Yes, screen. Screen. I don't want to scream. Share entire. Do you see my screen?
Not yet.
Okay, sorry, Rachel. First time round. And share entire screen. Okay, got it. Okay, play. Play
There we
slideshow.
go.
Say.
Okay,
Wait, I
I
want
get
to
it.
go back. Okay, so here we are. What we want to share with you today, super excited to be here. And what we want to share with you today is getting started with Google Confidential VMs. And as Rachel mentioned, it's Jerry and Malini here with you today. So just a little rewind. Why are we here today? Why do we care about confidential compute? It's to protect sensitive data. It's your personally identifiable information. It's any special IP you have. It's your crypto secrets, all those private keys, financial data, healthcare data, customer data, name it. Data is precious, okay? Another important thing is a lot of workloads are running on shared infrastructure, public or private clouds. I mean, you can have your competitor on the same physical host or in the same data center, and you want to protect your resources from them. So in this land of shared infrastructure, how do you give some more security? And last but not least, it's regulatory requirements. You can't process credit card data or healthcare data or some government tasks on just about anywhere and everywhere. And these are the kind of things that Roman alluded to. You don't want to be constrained about where you're running what, okay? So confidential compute helps even that landscape. So you can run confidential workloads that are highly sensitive in more regions. But what else do we think about this? We think that confidential computing one day will be as ubiquitous as encrypted transit and encrypted storage. Do we think twice about using HTTPS today? No. Do we expect it everywhere? Yes. Any form submission, you definitely want HTTPS, and likewise anything storage, we encrypt it. So That's kind of the direction of what confidential compute is offering you, protecting data in use. So what does a confidential VM provide it? Roman went into a lot of details, but what I want to bring out here, the most important thing here is that it's the foundational building block. It's like the Lego block that you use to make other things possible in a seamless, easy way. So once you have a confidential VM, what do you get? It encrypts your data that you're using. It's impervious to the hypervisor that launches these VMs. It provides workload isolation, which is super important when you're in a node processor where other workloads are running. It also offers you measured launch. So in hardware registers, you can save everything you've downloaded and started executing on that VM. And last but not least, once you have something like measured launch, it's like a fingerprint, you can attest it. And those are the sort of things that Roman already alluded to with Trusty and Keylime and things like that. So fast forward, what does Google offer you? It offers confidential VMs. It offers something called confidential space, which is very similar to the Coco project that Roman alluded to. It offers you confidential clusters. That means a Kubernetes cluster where every node in there is a VM that's a confidential VM, and even services that are wrapped in confidential VMs. So you can have a database service or some other kind of service all inside a confidential VM. So let's keep going. I think it's important to walk through this little bit of block diagram. So a confidential space is a confidential VM. In our case, we're talking about an Intel TDX confidential VM. And then inside it, there's something called an operating system, your guest operating system, which in this case is a hardened OS that is just mainly for launching containers. So it not only has the operating system that's small, lean, mean, so therefore less, landscape there for threats, but it also has a container launcher in it, and that eases you to drop in a containerized workload. Why is that important for us? Because more and more workloads are offered as containerized solutions. They bring in all their dependencies, it's all working. Further, it's kind of like hermetically sealed. It doesn't let you do just anything and everything unless you're in debug mode. So you can't go and say apt-get install blah, blah, blah inside this VM because it's locked down. Its firewall is also locked down. So those are all the additional safety features of this. So we're going to have a demo. And Jerry's going to give the demo. Jerry's our security architect. He is the lead architect and developer for Intel's Trusted Authority. That's an attestation solution. And I'm just going to share with you what this demo setup is. There is a workload on the very left, which is running your task. And that's the one that we all have to agree on that can look at this confidential data of yours, your secret data. What is the secret data? It's income data about Alice and Bob. Alice's data is sitting in AWS, so it's in a different cloud. Bob's data, I mixed them up. Bob's data is in AWS and Alice's in GCP. Doesn't really matter where. But what's important here is to recognize that your data source that you want to protect can be in any cloud. The token to access it is federated. And so here's your workload, and then here's this authentication piece, the Intel Trust Authority. So what happens is on launch, everything gets measured, and then you not only identify that I am in this encrypted enclave, but I also am who I say I am. It's like I'm Malini with my DNA and my retinal scan sort of stuff. And what is this DNA retinal scan? It's like your fingerprint. It measures not just the firmware from Intel to create trusted execution environments. It measures the operating system. It also measures the actual workload running. Okay, with that, I hand off to Cherry.
Okay, thank you, Malini. Sorry, I was dropped out. The browser was closed suddenly. Lucky I come back. Let me share the whole screen. Can you see my screen?
Yes, we see recursive screens.
Okay, good. So thanks, Malini, to give a briefing of the demo scenario already. So just to keep things moving, I actually already launched this workload already. So this demo workload is running in Google confidential space already, right? So this is the container image running in Google confidential space. So as what Malini just described, so we have two data collaborators here. So one, Bob, he hosted the data on AWS, and Alice hosted data on GCP. So here I just will use Bob's data bucket on AWS as the example to show how the how the relying party data collaborator can use ITA token claims to define the trust policy. Before we dive into that, let me just show the cloud log, which shows the workflow of the workload itself, right? So here I'm actually in another VM, not in the VM of the workload itself. So I'm just using this VM to show the cloud log from that demo workload. So what I do is just show the log, which give the overall idea of the workflow of the workload, right? So basically, this workload is every 30 seconds it will take a attestation token from Intel Trust Authority. Okay, it will receive the token, which is a Google confidential space compatible token format. Okay, then it will use this token to access Bob's income data on AWS S3 bucket. Next, it will fetch Alice's data on GCP storage bucket. Then it do the comparison, right? So they output the verdict. So here I'm going to show how the trust policy will protect the data access, right? This is the trust relationship or trust policy Bob defined on AWS S3 bucket. So if we look at this, trust policy, we can say, it specifies the Intel Trust Authority as the OIDC token provider, right? Then it will define some trust condition here, specifically say hardware model must be genuine Intel TDX platform. The software name claim, which indicates if the confidential CVM image is a known good confidential image or not. By the way, Google provided the known good image ring for Intel Trust Authority. So we use that ring to verify the coming evidence to make sure it's a known good confidential space image. Then we have the most important one here is the workload identity itself, the image itself. We have the image digest, which indicates the workload Bob and Alice agreed upon to access their sensitive data, which is the income data, right? So for demo purpose, I will deliberately to modify the image digest here, right? Which will make it, unmatching with the running workload anymore, right? So let's see what will happen. Okay, policy is updated. It will, because it's a live demo, it will, for AWS, actually, it takes time for AWS to provision modified policy. So it will take some random type. Okay, connection fail. Okay, sorry, connection fails. Let me, something happens. It needed me to give
Okay,
a
while Jerry
single
is
sign on,
debugging
right?
this,
Yeah.
let me
No,
just share a few
it's just
important things. Okay, so first and foremost, when you have a token and you want to authenticate it and determine whether you want to release your resource, what are the things people care about? The freshness of the token. So one of the things ITA provides is a nonce, like, is it really, really fresh that you just attested it? Another very important thing is, let's say it's accessing this income data, you might want to say, who's allowed to access it? Maybe it's only the HR department. So something associated with the user's role is also something that the policy can determine and say yes, no. And as Jerry also pointed it, is it a rogue workload or is it the actual workload that both Alice and Bob have agreed upon? This, income comparative workload with signature XYZ that's in Docker Hub somewhere. So you get to specify a lot of things in the policy so you can really harden the access to your confidential, your secure, your secret data, etc. Okay, so Jerry is making progress already. And a very important thing is these policies can be dynamic. What Jerry is demonstrating is changing the workload signature that he will allow accessing the data. And he says, okay, look, within a few minutes, the gates are all locked. You can't access this data anymore.
Yeah, thank you, Malini. Rachel, and as Laura said, it takes time for AWS to provision the modified policy. So obviously, it's not provisioned yet. So let's see. Oh yeah, okay, coming. So you can say, the modified trust policy has been deployed. If we look at the workload, it is still receiving the attestation token from ITA, right? So say it is still receiving the token. But if we look at, the data access, when it tries to use the updated, attestation token to access Bob's data, it's denied, it's rejected because the new policy, the attestation token claims doesn't match the image digest specified in the new policy anymore, which hereby, this access is denied. So this exactly shows how the, inter-trust authority token claims can be used to define the trust policy on AWS, which is used to, control the data access. The same thing for GCP, it's just about the different location where to define the trust policy, but the overall concept is exactly the same, no matter it's AWS or a GCP. So if, this is a GCP identity pool where we can also define the similar trust relation conditions here. It calls attribute condition, but it's basically the same thing. So here, this is a quick demo to show, how inter-trust authority can be used as the independent attestation provider for those, confidential environment on GCP. The same thing for Azure. We actually enabled Azure as well. So we have a technical white paper published here. Also, the link is also included in the presentation, where we provide deep dive details how Intel Trust Authority was integrated with Google Confidential Space to provide the third, independent attestation service for those GCP Confidential Space applications. Any question?
So there are questions. Let me see here. Hold
Okay.
on. 3 minutes ago, can we build the image locally to replicate the digest?
Build the image locally to replicate the digest.
So
What
you
that
can
mean?
go on the Google Confidential Spaces site. They offer their own hardened OSVM image, but you're able to bring in your own images if you wanted a Ubuntu or SUSE or some other image. So in that scenario, you would bring your own image and then you would have to publish your own digest because that fingerprint involves, the whole stack. But yes, you can.
And then we have one other one. Oh, go ahead, Jerry.
So when we see image, there are two images here, right? First one is the confidential VM image, right? Which is the OS image, which provided by, what they did, they published, say, this is you can still see my screen, right? So this is the image I specified for this demo workload. This image is published by Google. They provide the RIM. They published the RIM. We ingest the RIM back into Intel Trust Authority to make sure, this image is known good image, right? So this is the confidential space, the CVM image. Here, when user launched the workload, they needed to specify the container image. This is from user or customer. They specify, where to fetch the container image. So in the confidential space, the image, there is a built-in launcher. They call it a trusted launcher. So everything is measured to the TDX, right? RTMR register, including the OS image itself. Then, their launcher will measure the image itself to the RTMR as well. So the whole chain of trust are measured to MRTD and RTMR. So with that, ITA is able to, verify everything and, issue that as claims in the token itself. Then later, blind party can use the ITA token to verify if the entity can be trusted or not.
Great.
So, but was the question about the container image, the application image, or the VM image? So you can, of course, bring your own application image. That's the container. And then the actual confidential VM, you do have the ability to tailor it for your own OS and other stuff.
Right.
So it's Edward that's asking these questions. Thank you, Edward. So he's asking, is the Google image closed source?
So the Google confidential VM image is open. It's based on their Chromium OS.
They if you know the Google Cloud, right? They call it a container optimized OS, the COS, which is, I believe, is a container Ubuntu based. But they have
They
their
say it's
OS
the
image.
Chromium based OS, and they have a
Chromium
GitHub
OS,
too.
container optimized OS.
Okay. We're just because we're running behind, I am gonna move us along. If you two would take a look at the chat and answer the public chat, that is, and answer any questions, I would appreciate it.
Yeah, sure.
Okay.
But thank you so much. Really, really good introduction to this area. I think it's just going to get bigger and bigger. So I want to thank you both. I really, really appreciate you coming by. Okay, Steve, hello. So thanks for hanging in there. It was a rough start. Okay, so Steve is here from Anjuna Security, and they are actually sponsoring this event. So big thank you to them. They have some really, really interesting technical pieces of the puzzle for confidential computing. And I'm super glad that Steve is here today. He is actually the CTO. He was previously also with Automation Anywhere and Experian. And so a lot of times when there's a newish technology out there, people are kind of like, but where do I use it? So what Steve is going to do is give us 3 confidential computing use cases so that we can see really when, where, and how people are using it. So I'm going to pop out, Steve, but thank you. And thank you to Anjuna. And I'll pop back when we're at the end. Bye.
Thank you, Rachel. As Rachel said, I'm Steve Van Lare. I'm the CTO for Anjuna Security. And our next speaker will be coming from Oracle. And that's also in my background, as well as Boeing. I've done an awful lot of work in defense contracting, security, and AI through my career. And they all sort of come together in confidential computing. So as Rachel said, I will be talking today about how confidential computing can make a real difference in the value of the applications that people are deploying in the real world. As Anjuna, we are connected with the Confidential Compute Consortium. If you don't know about them and you're interested in confidential computing, I highly recommend you check it out. We also work a lot on the regulation side with CSA and MITRE to help the evolving landscape of how confidential computing is used and managed. So the first place I want to start is confidential computing involves 2 new capabilities in the CPU. One of them is isolation, and this is pretty easy to describe. Pretty much any application, any agent, any service, anything that's running on a CPU, if it's working with encrypted data, it's got to decrypt the data to make use of that data in memory. And while things are in memory, they're exposed. And we long ago started encrypting hard drives. We long ago started encrypting the network. The last thing we need to do is we need to protect the applications. We need to isolate the applications when they're running in memory. And so confidential computing was created by the hardware vendors, IBM, Intel, AMD, NVIDIA, ARM. They've all created capabilities that enable us to isolate and protect our applications from the kernel, from bad actors, from anybody else that we don't want to have access to the things that are there. All of the clouds support confidential computing. Question I get a lot, how do I get my hands on this stuff? Pretty much any cloud instance you want to work with, you can get at Azure or Google or AWS, IBM, Oracle. It's all available in the cloud today for your use. So isolation is the first thing that we need to focus on. The second is trust. So attestation is a process for proving the code you put into an isolated space is in fact the code you intended to put in that space. So once I know I have the right code in the right place. I have a guarantee of trust. And confidential computing, in part, enables you to reason about a smaller space and make claims about the security. And so, one of the types of problems that people want to solve is a data problem. You have data, I have code. Can I have your data? The answer to that question is usually no. You can't. We don't want to share PII information. We don't want to share sales information. We don't want to share models because there's a trust problem. And confidential computing is targeted at solving those trust problems by using attestation and isolation to be able to mix these things together in a safe way, to have an escrow space, if you will, in the enclave to do what we need to do. So here at Anjuna, our goal is to ultimately make confidential computing just simply computing. Drop the confidential. It is the default state in the future, we believe. And we want to make sure that this trust and isolation that you want to take advantage of is frictionless. So the first part of our tech stack enables you to build images wherever you want to build them in your system, separated away from everything else. And then the second part of it enables you to run those instances. So we'll support whichever cloud you want to use. We'll support whatever on-premise instance you want to run. So you target the application, you target the environment, and then off you go. We want to make this incredibly simple to use. Because if you do that, if you make confidential computing simple, it has the ability to protect not just a single CPU, but you have real end-to-end protection. You've got protection in memory when your application is running, whether it's an agentic process, whether it's a clean room application, whether it's an application you're trying to prevent attacks against, whether it's a high performance compute solution. All data is born in memory. It's protected there. You load it into a TLS transport, send that over the wire to another box that's also protected, and you can keep truly end to end your entire application and your entire estate. So we've talked a bit about confidential computing. Let me talk a little about some real world use cases where people are using this today to gain significant advantage in their applications by taking advantage of trust or isolation or both. So the first I want to talk about is an example of a bank that wants to isolate their cryptographic services to speed up their go-to-market. So why would you do this? Well, we all put our keys in an HSM somewhere. It's locked. We've got a hardware module that's protecting the keys. But as soon as you move the keys out of that into some sort of infrastructure, that data is exposed. And that presents a risk to the overall business. So what a lot of organizations do is they then take their cryptographic functions that are going to work on those keys and do that work, and they isolate them on a separate network. Perhaps that network is sitting on-prem somewhere so that it can get some isolation guarantees and get some protection guarantees. By using confidential computing, by moving that into the cloud, you can move the cryptographic functions next to the applications that are using those functions. And you can gain significant performance improvements in your application, as well as getting significant advantages of isolation and trust and security for your applications just by picking those cryptographic functions up and isolating them a different way. Instead of putting them on an air gap system, instead of putting them in a isolated on-prem solution, you can move them where your compute is actually used. And so this gives you the ability, this gives the bank the ability to move faster and to be more nimble in their activities, which is why they're investing in this and why they are doing this. The end result, they have minimized greatly the exposure of PII and keys in memory for various operations, be it PCI or just processing whatever privacy information the bank has access to. You have a longer key cache period because you've got significant improvement on the application, as well as the ability to not have to go back to the HSM so often because you've isolated the data and you've isolated the cryptographic functions. You've cut out a tremendous amount of insiders from the circle of trust, because somebody who manages the system doesn't necessarily need access to the memory in these systems. So by eliminating those attack surfaces entirely, you can really increase the integrity of the overall system and what you do. I have a picture of what this looks like, but I think it's even simpler if I go through an example. So let me switch my screen here real fast. And let me do a walkthrough of what this looks like. So the bank may have processing kind of around the globe. I'm going to focus on a UK data center, and they've got data running in a variety of different clouds, whether it's AWS, Google, or Azure. And the way their functioning is set up is when a user dials in, they hit the application in the cloud, which then it bounces against the on-prem data center. And the cryptographic functions are living in that data center. So while all these applications are there, the performance penalty is the fact that you hit a processing system or you hit a fraud prevention system or you hit a payment system, and you have a lot of back and forth to the on-prem data center, which turns into a real world cost to the end user. So by picking up those cryptographic functions, moving them into the cloud, protecting those with confidential computing, you're able to fit in a lot more processing in the same amount of time, and also reduce the amount of time that the end user is waiting for a process, because you don't have to go back to the on-prem systems for every single request and go get those cryptographic functions performed. So this is what the enablement of confidential computing is doing for the bank. It is significantly improving the performance of their applications. It's enabling them to put more applications in stream with individual requests while providing all the isolation guarantees of what they're after. So let me talk about a different use case now. Second use case, a different bank we're working with, and they have a long history of data with their customers. And in particular, what they wanted to be able to do is they wanted to use purchasing information to provide targeted offers to their customers. So for their high worth customers, they wanted to understand their purchasing trends, understand what they're doing, and then make special offers for those customers. The challenge is they needed to combine data from a variety of different sources to be able to pull off this activity. The joins are pretty straightforward. Pretty much any intern computer scientist can join from table A to table B and make the offers. The challenge is a risk problem. Do we really want all of this data exposed in one place? What they needed to do is they needed to have customer data from the bank, including their history with their balance and the various account information that the bank has. And they needed to pull some retail partner data together and merge that with some AI models to drive some new activities and new results. And this is hard to establish the trust. And confidential computing, the ability to run these models in a space with the data where the model owner can't get access to the data owner can't get access to the model, but we've isolated off the actual compute, enables driving business outcomes that they couldn't achieve before without confidential computing. So this clearly lands in the space of new use cases, new things you can do with confidential computing that you couldn't safely do without confidential computing. So this particular bank got significant increases on their ad spend. They were processing millions of transactions a day. They were doing a tremendous amount of inference, significantly reduced the exposure of PII risk by moving all of this into confidential computing. Even the people running the system don't have access to the data, don't have access to the models. So this gave them the ability to really test out and work with their partners to establish a better business outcome because of the abilities that confidential computing gave them. Last one I want to talk about is AI and agentic AI in particular. LLMs have essentially cracked the NLP problem. So natural language processing is now within scope of what we can solve with computer science. And everybody's excited about what you can do with LLMs, but thinking about what you should do is a much harder problem. LLMs are non-deterministic in terms of what you get as a user. So if I put a prompt in and I ask an LLM to go give me a result, I won't necessarily get the same result each time. Any of us that are demoing with LLMs know this means every time I do a demo on an LLM, I may get a different result and I may have to stay on my toes in terms of what I'm doing. What we're doing with customers is providing a trusted execution environment space for a supervisor model. So let the agent be the agent, but bring the supervisor into its own space. And by protecting that supervisor, we prevent it from being tampered with. We prevent the prompts from being modified. We enable it to focus on what should you do as opposed to what can you do. And it's going to supervise the behavior of the agent itself. So you have a place for both static and dynamic rules to be executed, and it can see into what the agent is doing and make decisions about whether this is appropriate or not. So with these adaptive supervisors, you can match the flexibility of the agent with security policies that follow in line and are focused on doing what the agent should do. So what does this look like? It looks like a pretty straightforward injection into the middle of an agentic model. So the separations of duties live by the fact that the agent itself, you let your developers develop the agents. So the folks that we're working with on this, they're going to put an investigation together that says, investigate the root cause of this failure. I'm looking at the logs. I then want to go look at a knowledge base, make some decisions, take some actions. Pretty straightforward use case today in the agentic world. My time and automation anywhere, this would be an RPA use case that would be pretty common for what you can do. Well, the separation of duties, what I want is a second agent that has a policy that's determined or a prompt that's determined by the CISO policy. It's going to have access to the context of the agent. It's going to have access to the prompts of the agent and what the agent's attempting to do. And it will ask a different question. As a CISO, I want you to look over this agent and make decisions about what's appropriate or not. And that agent manager is going to provide access to tools. The agent manager is going to provide access to data to the agent. So you don't have to give credentials to the agent. You can give the credentials to the agent manager, which is running in confidential computing, and it's going to make a zero trust decision based on each request. Just because I gave access to 10 minutes of this log file a second ago doesn't necessarily mean I'm going to give another set of access to that log file if in fact I think the agent doesn't need it anymore. And so the agent and the agent manager will have their own dialogue back and forth, with the agent manager kind of looking over this intern of an agent and protecting what it is doing. So this model is one where we use confidential computing to provide a trusted space for managing the agents and supervising what they do. So overall, we believe very much that confidential computing can be both low impact or low effort and high impact. Make it very easy to get applications into confidential computing, do it significantly faster than rolling up your sleeves and trying to get to core first principles, as well as the impact it can have on the business in terms of reducing how many MITRE attacks do you have to worry about, increasing the amount of revenue you generate, increasing the performance of the application, and getting there quicker. So that's what we do, and that's what we focus on, and that's what we think confidential computing has the potential to deliver to the industry. So thank you very much. I'll leave this up here. There's plenty of links to figure out free trials, data sheets, white papers, walkthroughs, anything else that you may need.
Amazing. Thank you so much. We will be sending around an email after with some links so that people can get there very easily. But that was great. And I really love we think confidential computing should just be computing. So I think that's
Absolutely.
great. All right. Thank you. Thank you. Thank you so much. And we'll be talking soon.
Okay.
All right.
I'll respond to questions if there were any in chat.
Thank you so much.
Good morning, everyone. So, first of all, thanks for having me. Second, I can't agree more with one of the sentences that I heard on the presentation before mine. Confidential computing, in my mind, in 10 years from now, 10 is arbitrary, can be a little bit less, a little bit more, will be the standard. There is not a good reason why to don't use confidential computing in everything. Why this is even more important right now in the age of agentic AI? We are moving from a situation where AI was generating content to a situation in which systems don't only generate content, but they take action. They execute. On what they execute? Guess what? On data. So the big challenge that we have right now with agents is that an agent, to make a smart and informed decision, must get access to data that sometimes are sensitive. So we are, at the same time, exposing ourselves to great potentials, but also to great risk. It's very interesting to see how autonomous agents are crossing the boundaries between organizations and between companies sometimes. So what is really happening is that we have an emerging gap. The gap is that the agentic workflows, given that they are interacting with systems, taking actions, sometimes making decisions with a human in the loop or without a human in the loop, they are really empowered now. The big challenge that we have is that every time that we talk about an agent, we're talking about live data and not anymore static training sets. To make it clear, so when you train a model, if you want to use sensitive data and you want to redact this data or mask this data or use differential privacy, you can still get a good level of protection of your data. You can keep strong data sovereignty, but at the same time, you are not really leveraging in many cases, except some cases like healthcare and some specific fields, you're not leveraging too many sensitive data to train this model. An agent must make a decision, whatever is the field, customer support, or think about negotiation, think about refounding a product, an effective product from customers. They need access to this data. So the problem that we have is that we need to be sure that these data are floating between systems in such a way that they are not exposing the loss of this critical information in any situation. Agentic AI, you can think about a read-write act where the systems can perceive something through data, through systems, through environmental data, reasoning, use a tool, and then make a decision and act. The confidential computing aspect of it, it's a way to protect data when they are in use. And the presentation before mine went deep into why confidential computing is so powerful. With this being said, you can get to a zero trust agentic AI situation and requirements by moving beyond network trust and start verifying the code identity. When you verify code identity, you can use remote attestation to be sure that the different pieces of software that are supposed to act on that data are genuine and are the ones that are intended to operate in that field. There are three different layers that we have to consider when we want to implement a sovereign agentic AI system. First one, we want to secure the conversation. What does it mean? This means that you want to be sure that there is an interoperability layer, that is usually model context protocol, that enable systems and agents to communicate securely and to pass context between components. These can be enhanced through identity and governance frameworks. For instance, agency, manage agent identity, permission, and create also a sort of scoring mechanism that can help you, actually, that can help other agents to understand if they can trust other agents. At the same time, can enable you to basically determine if with a specific layer of, with a specific level of trust, your system can interact with other systems. The limit is that although you are securing the conversation, you are not securing what is happening in the brain. And by brain, what I mean is when the agent is making a decision, maybe he's invoking an LLM or using an LLM as a judge, doing some decision-making through the human in the loop and through live feedback. So while MCP ensures that the data are transmitted correctly, agency ensure that you're talking to the right agent, The problem that you have is that data are decrypted in memory and then they stay unsecured, and they are exposing you to the failure of traditional defenses. Data masking fails for agent because an agent needs semantic context to make decisions. So if there are no data, if these data are not visible, it's really hard to get any value out of from an agent. You can use homomorphic encryption, but it's, from my knowledge, at least 10 times lower than traditional encryption. At that point, you can ask yourself two questions, right? If your system is not real time, you may have batch work, or you can have some acceptance of delay that can help you. Still, next it's significantly slower. The other problem with homomorphic encryption is that right now it's pretty secure, but we really don't know what will happen with quantum computing. My guess is that many of these, actually it's not my guess, my strong opinion is that many of these techniques will become obsolete right away when quantum computing will be available to a wider group, to the population, to malicious attackers, to hackers, to everybody. So the reality is that with the traditional defenses, you are leaving some data in clear text in the RAM, and this is the most vulnerable state. Think about this state as a de facto state that you should protect in very specific contexts when you are dealing with PII, PHI data, and any sensitive information like HR, customer profiles, and anything that can be used to hack the life of somebody else and therefore to compromise their digital dignity. There is also another big problem with quantum computing. There is now a sort of going on initiative, if we want to call it like this, where adversaries, hackers, or malicious organizations are harvesting today's traffic, although it's encrypted, because at some point they believe that they will have the sufficient computing power to decrypt that data later. So when quantum computers will be widely established, we're talking about 2030, 2035, that's again, it's an estimated range, can be earlier, can be later, I doubt, but sooner rather than later, you will see that all the current encryption keys will be broken, and easily to be broken means that all the data that have been harvested will become potentially decryptable and will expose major companies, people, to the loss of several information. That's why it's important to think in an agentic world to introduce as soon as possible countermeasures to protect the data and the digital dignity of your user. The mitigation can be definitely to use hardware-encoded sovereignty. This means that you will use also with agentic AI and with agentic workflows, confidential computing. Now, there are companies like Anjuna, like Opaque, many others that are building solutions to support these use cases. And I'm not saying that I don't want to diminish their impact at all. But at the end of the day, you can get to a confidential computing architecture pretty, I wouldn't say easily, but following some steps, you can build your own. So this is to mean that you don't have to think only about getting in front of huge cost and a huge investment, and you should start to think about trusted execution environment, attestation, and tamper logs, and all these aspects in your agentic systems since the beginning. You can design it with this principle in mind, and then you can involve experts or service providers when needed. The typical sovereign workflow, when you want to secure multi-party collaboration, it's when an agent starts to negotiate something with another agent. Let's think about a supplier agent that is working with a buyer agent to secure some material or some procurement based on sensitive forecast data. At that point, you are going straight into the confidential computing realm, in my opinion. Because if you use a trusted execution environment to process all these data, when the data enters the enclave, are decrypted in the CPU, so it's only visible to the silicon, the agent can start to reasoning on top of clear text without exposing the data into the RAM that is accessible to different components, to some extreme to an hypervisor, to a cloud provider. And then when the data are re-encrypted, you are basically observing a workflow that keeps the conversation confidential. The value is that the collaboration starts to happen inside an environment that is not visible by any of the other parties. There is an exchange of keys, but at the end of the day, the keys remain owned by one of the parties. This means that through a little bit of sophistication in your architecture, you can protect the sovereignty of your data and the digital dignity of your users since the beginning. You have to implement at least 3 layers to keep your architecture highly trustable, with a high level of data sovereignty, and with a high level of security. You can use a layer for governance, permissions, and agent-to-agent verification, and you can use framework like Agentic. You can use model context protocol, that is now a de facto standard when systems have to communicate and share context over the internet and inside their flow. And another layer for computation should be implemented through confidential computing so that you can isolate your data. These provide governance and verification for the Internet of Agents, including cryptographic identities, delegation chains, and reputation systems. With these 3 layers in place, you can secure your agentic workflow and reduce the risk of losing any data. Security, in my opinion, is part of preserving digital dignity of people. Digital dignity is the user's fundamental right to control their digital self-intent, understand where their data are shared, how they are used, and so on. If you think about digital dignity when you design a system, you are starting to do a very straightforward usage of ethical principles that belong to what is known as ethical AI. Privacy by design, it's one of the most important ethical aspects of AI that should be implemented in every system at any level. So my call to action for you is to build agents that are secure by design so that you can protect the digital dignity of the data that they touch. And the systems should be grounded on ethics and therefore digital dignity by definition. Thank you. Happy to connect over LinkedIn if you have any question, any follow-up, or any feedback.
Thank you so much, Giorgio. That was really great. Appreciate your time putting that together. Yes, we will have everything. Everything will be on YouTube. I'll make sure that we have links to everything. So we'll make sure to get the word out. Thank you very much.
You're welcome. Bye.
Bye. Okay, and we have next Giovanni Mazzeo. Let's see if we can show him on the screen. There
Hello.
you are.
Hello.
Great. Okay, so he is from Trillion and reached out to him and he had a good idea for a session. So here he is. So he is going to talk about trust without compromise, enabling verifiable DEXs with TEE technologies.
Today we discussed, first of all, who am I? I am Giovanni Mazzeo. I am an associate professor at the University of Naples Partenope, and at the same time, I am chief scientist at Trillion, a company that I co-founded with some people. And we are a company that is trying to provide, in the space of Web3, trying to enable a high-performing, verifiable, decentralized exchange. So today we heard a lot about the use cases of trusted execution environment, something like, for example, AI. And here in this presentation, we are going into the details of another use case, that is the usage of trusted execution environments in the Web3 context, and in particular for securing a decentralized exchange. First of all, let's understand what is the context. So in the Web3, there is this situation where the market share of decentralized exchanges is rising. The forecast is pretty promising, against those that are centralized exchange. Centralized exchanges like, for example, Binance, Deribit, just to make you an example of some of these centralized exchanges. And why is that? It's because a decentralized exchange provide more trust to people, since there is no need to trust a central entity. And in the Web3 space, this is very important because you want to always have a very decentralized property in your solutions. However, there are some limitations in terms of performance. In particular, so decentralized exchanges should rely and depend on the performance of the blockchain. And this is the blockchain is known to be low performing, especially L1 blockchains like Ethereum. And these, of course, entails issues to the user experience, and in terms of, for example, delays for having a confirmation of transactions, delays in particular in moments of congestion, which are the most critical moments. So when there is a shocking event, the Ukraine war or whatever, and so people, there is a high flow, a high volume of trading, people want high performance, and they want, and the timing there is very important, because that could affect the economic, of course. So what is the idea is that we should balance between performance and trust. There was the adoption of roll up, the so-called L2 blockchains, so blockchains that are batching transactions, and then these transactions are relying on the L1 blockchain. But in this case, again, we are gaining in terms of performance, but we are again centralizing. So we are, for example, using units that are called the sequencers, matchers, engines, mempools. Now, don't care too much about the technical details of this unit. What is important is that you realize that we are increasing in terms of centralization, and but gaining in terms of performance. So of course the sheet is short, and there are, of course, different risks in this situation, because the sequencer, so these central points could change the order of transactions. So I am a trader, I make a trade, then there is another trader in a different instant of time making another trade. If those trades are changed in terms of orders, that could have a sort of impact for the financial return. Then there are possibility of selective censorships. So someone could apply censorship policy. So there are risks from the financial point of view that are that are pretty important. And as I was telling you, there are different kind of these risks, and all of these, of course, entails a money loss. If we centralize execution, we need to find a solution. So we want to centralize a bit the execution using these L2 solutions, but we need to protect these solutions. And how we do this? We do this leveraging trusted execution environments. So trusted execution environments to the rescue. In this case, we leverage, especially, we are not caring much about the confidentiality. So as you know, the trusted execution environment can be used for providing confidentiality of data and code running inside it, but also to prove the code that is being used, that is processing the data. So the idea in Trillion is that we leverage the trusted execution environment, especially for integrity purposes, and to demonstrate to customers that the code that is processing their transactions is actually what is the code that we have open sourced, that they can trust. And so they have a proof, a so-called proof of code, and so that there are no risks of changes of orders of transactions and so on. Of course, how we do this? We do this by leveraging the attestation features of trusted execution environments. So the architecture of Trillion is this one. Now I'm not going into the details, but just to let you understand that what are we doing? We are essentially leveraging a set of decentralized sequencers, so these important units of these L2 blockchains running inside the trusted execution environments. And in this way, we are capable of providing that guarantee to our customers. Now, one point. So as you understand, context has a pretty strong security requirements. And we had a lot of questions from investors regarding risks of trusted execution environment. So the trusted execution environment is not the panacea. We know that they have a certain threat model that they can't cover against certain risks. And so first of all, there is the one main point that you need to trust one vendor, one technology provider, one manufacturer. Then there are all the side channel and micro architectural attacks risks. There are, of course, physical attacks that can be made against the trusted execution environment. There is one that was recently published that is very widely known, that is called the te.fail, and you can also visit their webpage, where they prove this. And this was one of the attack that was discussed with the meetings that we had with investors. And another point is that with the attestation, we cannot prove the ownership or the location. We can prove the code, but not the location. So in Trillion, what are we doing? Given the context and given we smelled this need of additional trust from customers and investors as a consequence. And so we decided to set up some sort of approaches. First of all, leveraging multi-vendor diversity. So leveraging multiple trusted execution environment technologies, VM-based trusted execution environments that rotates among themselves and provide more guarantees against specific vendors' risks that could happen. Then providing so-called platform ownership assurance. So we are leveraging some state-of-the-art research works that can be used to give a proof on the data center where these trust execution environments are running. And this is needed because we want to give, let's say, insurance to our customers that the physical security of the data center, so that the trusted execution environment is inside, for example, Azure, AWS, where they know that there is a certain physical security made on those machines. And last but not least, we are leveraging a hybrid approach that is a sort of backup layer, a ZK-proof correctness backstop, that we call it this way, where we can, let's say, asynchronously provide a verification with zero-knowledge proofs on the transactions that were made. Why we need to do it asynchronously? Because one of the main property and one of the main narratives that we present in Trillion is that we achieve instant finality and we achieve 100 transactions per second. And we can do this exactly by removing a certain slowness that comes from, for example, consensus algorithms, because we prove the code, we leverage the trusted execution environment that is being used. And so we are setting up an asynchronous solution for providing additional guarantees to customers that require a certain level of guarantees, but at the cost of performance. And I won't go through the details of the solutions, but of course, feel free to ask any other question that you want, and in case I can provide the reply. Anyway, the website is there reported, and my mail is there in case you have questions or you want to discuss some topics or research topics. We are happy to do it.
Thank you so much. That was really great. Yeah, we're going to have all of the sessions on YouTube later today, and we'll have links to everybody's, places, slides, all of that good stuff. So yeah, thank you very much, Giovanni. That's great. So
Thank you.
it's been really great seeing all of these different perspectives, all of the different layers that, let's see, sorry about that, have been here. I think there's a lot to learn in the confidential computing space. I'd love to know what you want to see next, what we could do next, in terms of content. But I want a big thank you to all of the different speakers. Thank you to Anjuna. And you'll be seeing more in this space, probably from all of us that were here speaking. And I want to thank you for joining us today. Have a good one.